Why is energy so useful in solving certain types of problems? How are energy and force related? This is obviously an introduction to a new unit, work and energy. This begs the question, why are these two things grouped together? I'll give you a lot of insight into the answers to these questions, and these two questions, why is energy so useful in problem solving, and what's this relationship between energy and force? Keep these in mind during the entire unit. This is obviously a video tutorial, so I won't be offended if you manage the video. I'm not here to listen, so if you manage the video, that means you're doing all these things. You're going to replay, you're going to pause, you're going to slow down if you need to, and speed up. This is meant to help you with the work and energy mental math worksheet. It's a deceptive worksheet. It's meant to be mental math, even though some of it might seem like trig, but we're focusing on the relationship between work and energy in that worksheet. This sort of goes with the roller coaster loop introduction worksheet. The idea is when you see a problem on the AP exam or any problem, I would say especially the AP exam or the mid-year exam, you're sort of confronting, like, how do I approach this? There are many perspectives. We've learned kinematics so far. Pause the video and think about, what are these other arrows? Like, what are these different perspectives? What do you know about? Pause it, think about it, maybe even talk about it. Okay, these different perspectives, as far as I'm concerned, throughout the year, like, I'm not talking about situations where we have, like, electricity or fluids. These are physical, mechanical things, quote unquote. That's not a rigorous definition, but here's my different approaches. You've got torque and rotation, which we haven't learned about, not to be confused with circular motion. So the torque that's involved in rotation is different. When you see a problem, you're going to be confronted with that. Work and energy is a big one. That's what we're learning about now. Dynamics, Newton's laws. Momentum, haven't learned about momentum yet. And this is my point in bringing this up. I personally prefer work and energy. I personally prefer this one. There's something about it being scalar. But a word to the wise, just a heads up. A lot of people have trouble conceptualizing it because it is so abstract. And because it's harder to draw. You don't have arrows to draw. Like you do in kinematics and dynamics, you can draw the forces. In kinematics, you can draw those, you can list your knowns and unknowns, and there's a sort of visual nature associated with the equations. People have mental models of those. Work and energy, it's harder to have a mental model of it. It's harder to have a mental model of elastic potential energy. Okay, pause the video in a second. Pause the video in a second and just talk amongst yourselves. Think out loud, shout things out at the screen, but give me different types of energy forms, energy types. People. I'll give one right now. People say kinetic energy. Okay, good. Now go. Pause it. All right. Here's a bunch. You just had a discussion. You shouted at the screen. It was like certain cult films where people go do these screenings and yell at the screen. Here's a list from last year. These are a bunch of things people said. You can read all those. Yep. It's pronounced nuclear, not nuclear. Here's another list from the previous year. And I want to show these relationships, like gravitational potential is a type of mechanical. Kinetic is a type of mechanical energy. Elastic potential is a type of mechanical energy. And I'm highlighting certain ones that I'm highlighting mechanical, I'm highlighting kinetic, thermal, gravitational potential, and elastic potential. Yeah, people try to get fancy and say stuff like dark energy and matter. A good way to say this is these are types that we associate with mechanical things. Like I think about moving machines and gears and springs and elastic bands and things of that nature. What is work? There's two definitions. This is Turgeon's kind of conglomerate of different things I've read, but it's a transfer of energy by means of a force. Now, I want you to really think about that and absorb that right now, but it's really going to make more sense as we do some stuff with that. But there's a force occurring and something's moving. Write that down. Something's moving through a field or through space, and energy gets transferred from the sort of agent, the object that is doing the action, and the object that's sort of receiving the action. And here's a mathematical distance. It's a product of force and distance, but be careful. It's only the parallel component. And here's the equation. Notice we're saying, obviously this is work. Notice that we're saying that that's not watts, that's work. It's a scalar quantity, by the way. You should write that down. It's a scalar, even though force is a vector. What we're saying is there's only a certain portion of the force that actually does work sometimes. Sometimes. Let's look at an example. Let's say me and my brothers are pushing a car. My brothers are mischievous and like to give me a hard time, and let's say the car broke down and we're all going to push it. 3 people pushing on a car. This is supposed to be a top view of a car that I drew when my board wasn't working very well, so it's very choppy. Rank these forces in the order. Let's say they're all equal. I put the congruency slashes. Which ones did the most work and which ones did the least work? They all moved it over this distance, which I'm representing with this displacement vector, this dotted line gray vector. This is a displacement vector. Now, my brother Dave would probably be at the drive at F2, because F2, he's going to help push the car, but he's also steering. My brother Mark is going to push on the side of the car because he likes to torment me and us and to be mischievous. And I would be in the back of the car just trying to directly push it. So pause the video for a second, and hopefully somebody's in charge of this. And pause the video, think about which you think did the most work. All right, here's the answer. F1 did the most work because F1 was the most directly parallel to this very displacement. See, totally parallel. F2 did the second most amount of work because, look, part of it is parallel. You would use cosines because usually you look at this angle right here between F2 and the displacement. F3 did the least amount of work, and in fact, F3 did 0 work. 0, ask yourself, how parallel was F3 to this displacement? The answer is 0. F3 was not at all parallel. And go ahead and take the cosine of 90 and prove it to yourself. I want somebody to literally get up with a book and start lifting it and doing stuff and stand there awkwardly in front of the class. Pause the video, get up there. Lift a book, but focus on the lifting, not the carrying, not the holding, not the like moving around and sort of the motion from like hip level or whatever all the way up to shoulder height or higher. And we're trying to develop a general rule about the work done by gravity. So here's how I'm going to explain it. When this person's, and they can continue to do this while I talk about it, but when this person's lifting the book, their force, the force applied, or normal if you want to think of the hand as being a surface, their force applied is parallel and in the same direction as the displacement of the book. That person did positive work. I'll say that again. The force exerted by the person and the direction, the displacement, are parallel and in the same direction, so that person did positive work. That means they gave it energy. They imparted positive energy. They didn't take energy away from the object. They gave the book energy. Conversely, or if that's the right logical term, the gravity is always opposite the direction. The gravity's down. So work by gravity is always going to be negative if you're lifting something. But the gravitational potential that was gained is positive. There's a system which includes the Earth. The book has energy stored in it by virtue of being in that system. Now here's a little note about identifying the system. It's just, you want to think about what's involved, the objects that are causing the motion, and that the motion that's being caused is kinetic energy and the position is potential energy, and this begs a question which we're going to debate and discuss later about, well, wait, what kind of energy was gained? I'm saying potential energy because the book is moving very slowly and stops. This is considered a conservative system because all of the energy is conserved within the system. We don't have to worry about going anywhere because of friction. Here's some slides. This is grayed out. There's information here. You can go back to this video and you can watch all this and write this down if you want. But I'm including it for information, but it takes a lot of explanation, and I hope you'll absorb all of this through doing problems and discussing questions. Here's another slide. All this positive, negative work stuff. Here you go. Work done to carry things. Very interesting. We'll talk about it more. Let's do an example. You can pause it if you need to, but I wouldn't necessarily try to do this example yourself. Let me just explain. It's good to look at the forces on the sled. So the dog's pulling the sled with this applied force F. And let's talk about the work done by the other two forces and the net work. And then I'll also talk about the energy. So the dog did 120,000 joules of work. The normal force and the weight did no work. The dog put energy into the sled. Okay, by virtue of the fact that the dog did work on the sled now has kinetic energy. It doesn't have potential energy because it didn't change its position in the gravitational field in the system of the Earth. It didn't stretch a spring, so no potential energy was gained. We don't have to worry about thermal energy because we're considering it a frictionless surface. So the net work that was done was 120,000 joules. Now, careful. The net work means the sum of all the work that was done. And there was no work done by gravity or the normal force. And when we do start lifting stuff, it's going to get weird. But pause the video maybe and just think about the fact that the force was totally parallel. 120,000 joules of work were done, and all of that became kinetic energy. Kinetic energy, level surface, no lifting involved. What if we're lifting something? If we're lifting something, this is considered to be the force diagram when you're told that you're lifting something. This is going to take some thought. You may be thinking, like, isn't the normal force going to be greater than the weight? Well, initially, yes, but throughout the course of most of the motion, it's the same, and then at the end, it's slightly less, so it all averages out, trust me. So the work done by every force individually. So the normal force did positive 38.2 joules because it's just equal to the weight. I know people don't like that, but it's true. Think about it. It's equal to the weight. It did 38.2 joules of work. That's the normal force. The weight did negative 38.2 joules of work. Whoa, whoa, whoa. Yeah, it makes sense because the weight was opposite. The weight force was opposite the direction of the motion. The object, the network is zero. Network doesn't mean it didn't gain any energy. It just means it didn't gain, well, I'll let you think about that. But it did gain energy. It gained 38.2 joules of gravity.